29 is where we're at in your unit 2 packet for review. Tomorrow's test, you only have a single period, so all you need is a pen, pencil, ruler, and calculator. I got it. Have a seat. All right, let's go. Page 29. Here we go. Don't ask me to repeat answers. I'm ready. You should be too. Starting on page 29. The variable t, you should know, stands for the term time, which is a scalar quantity, and it is always measured in the unit seconds, which we abbreviate with a lowercase s, not SEC, as some of you have been writing in your problems. It's an S by itself. The letter D, if it's a scalar, refers to distance. If it's a vector, refers to the term displacement, measured in meters, which we abbreviate with a lowercase m. V, when it is a scalar, refers to the term speed. When it is a vector, it refers to the term velocity, and it is measured in meters per second, which we abbreviate as m over s. A, when it is a vector, refers to the term acceleration. It will never be a scalar, and it is always measured in the unit of meter per second squared, which is abbreviated m over s squared. Okay, if we want to talk, I'm done reviewing. I'll just give you the test. But you are not here to talk while I'm instructing you and giving you review. If that's what you want to do, I'm done reviewing. I don't need to review. I'm pretty sure I'll get 100 on tomorrow's test right now. I'm not reviewing for me. Would you like to review, or would you like to just take the test tomorrow and I'll go on to unit 4?
I want to review.
All right, then we need to knock it off. If you think this is funny, Logan, you can leave. You should know that the term position is number 1, distance is number 2, displacement is number 3, speed is number 4, velocity is 5, acceleration is 6, and time is 7. There are 6 equations that you should be familiar with that we can use whenever we deal with accelerated motion. The first equation from your reference table, V bar is d over t. Here I've shown you how to manipulate it for both d and t. The second equation is one that I asked you in the notes you were given last week to add to your reference table. V bar is the same thing as VI plus VF over 2. When you have 2 measurements of velocity, to find the average of them, you add them up and divide by 2. This is not on your reference table, but you will be expected to know that equation on tomorrow's test. The third one from your reference table, acceleration is a change in velocity over time. I asked you to expand that on your reference table to show it as VF minus VI over t. That is how you get the velocity change. So the velocity change could be the acceleration times the time, or the time is the velocity change over the acceleration. The fourth one, directly from your reference tables, VF is VI plus AT. You should be able to move this around for any of those variables in that equation. The next is VF squared is VI squared plus 2AD. Again, you should be able to manipulate it for any of the variables in that equation. And the last one is D is VIT plus 1/2 AT squared. You should again be able to solve that for any variable in that equation. Next page. Let's start with the position time graph column, one at a time. So if you're dealing with a position time graph, the dependent variable is position, the independent variable is time, The y-intercept will be the initial position of the object. If the object is at rest, the graph looks like a horizontal line. If you are moving with a constant velocity, then you should expect to see a diagonal line on this graph. If you are accelerating, you should be looking for a parabola. If you are moving fast, the graph is pretty steep. If you are moving slow, the graph is fairly shallow. If you are moving in the positive direction, the graph will go up. If you are moving in the negative direction, the graph will go down. The slope is always representative of the velocity of the object. The area will never be asked for. I'm never going to ask you for the slope or the area. I'm going to ask you for the velocity, which you should know means you're looking for the slope. To find the displacement, you look at the change in the y-coordinates, either the rise or the drop of the graph between those two times. To find the average velocity, you construct a secant line and you find the slope of that secant. If you're looking for the instantaneous velocity, you draw a tangent line at that particular time and calculate the slope of that tangent line. You will not be asked to calculate acceleration from a graph of position time. All right, let's go to the velocity graph column. The dependent variable on a velocity time graph is velocity. The independent variable is time. The y-intercept is the object's initial velocity. If you are at rest, then the object would have a horizontal line drawn on the x-axis, or it crosses the time axis. That's when the velocity is 0. That's what it means to be at rest. If you are moving with a constant velocity, the graph would be a horizontal line, but it's either up in quadrant 1 or quadrant 4. It is not on the horizontal axis because that's where your velocity value is 0. If you are accelerating, the graph would be a diagonal line. If you are moving fast, then the graph is far from the horizontal axis. If you are moving slow, that's when the graph would be close to the horizontal axis. If you are moving in the positive direction, the graph would be up above the x-axis in quadrant 1. If you are moving in the negative direction, you're down in quadrant 4, below the x-axis. The slope of this graph always represents the object's acceleration. The area, if you were to calculate it, would represent the object's displacement. The displacement is therefore found by calculating the area between the graph and the horizontal axis. Another way to do that is to get the displacement by multiplying the average velocity by the time. And you would find the average velocity by taking the initial velocity, adding it to the final velocity for that time period, and dividing by 2. Or you could simply just read the graph at the middle time point. What I mean by that is if I wanted the average velocity between 0 and 2 seconds, the middle time is 1 second. I would read the graph at 1 second, and that gives me my average velocity. To get my instantaneous velocity, all we do is we read the y-coordinate for whatever time they asked you for the velocity at. And the acceleration, again, is found by calculating the slope of the line. All right, let's go to the next page, page 31. I'm going to do one column at a time, okay? So let's start with the velocity column. If you have no motion, it's 0. If you have a constant velocity to the right word right means the velocity is positive. If you're traveling with a constant velocity to the left, the word left tells you the velocity is negative. If you're speeding up as you go to the right, the word right tells you the velocity is positive. Speeding up to the left, the word left means the velocity is negative. If you're slowing down as you go to the right, the word right tells me the velocity is positive. Slowing down to the left, the word left tells me the velocity is negative. So all I look for the velocity is whether I'm going right, left, or I'm not moving. Yeah, make yourself a pass. All right, let's talk about acceleration. When you're not moving, you have no acceleration, Nikki. Yep. Acceleration is 0 when you're not moving. If you have a constant velocity, you have no acceleration, whether you're going right or left. Those are both 0. When you speed up to the right, remember when you speed up, the velocity and acceleration always have the same direction. Therefore, they would both be positive. Speeding up to the left, again, speeding up, they both have to have the same direction. Therefore, they are both negative. Slowing down, they have opposite directions. The word right tells me the velocity is positive, so the acceleration would have to be negative. Slowing down to the left, the velocity has to be negative because it's left. Slowing down means it's opposite sign for acceleration, which is positive. So see, we're hitting all the patterns that you should understand for tomorrow's test. That way you can just whip out those answers real quick because you've studied the patterns. Let's now talk about drawing the ticker tapes. If you're not moving, you just see one single dot. If you are traveling with a constant velocity to the right, we should have an arrow on our ticker tape showing we're going to the right, and the dots would be equidistant as I read them from left to right. If I'm traveling to the left, I need an arrow drawn to the left. Again, reading the dots from right now to left, those dots are equidistant. As I move to the right and I speed up, I need an arrow pointing right, and the dots should get further and further and further apart. When I go to the left, I need an arrow left. Speeding up, the dots should get further and further apart as I read it going to the left. When I slow down to the right, I need an arrow pointing right, and the dots should get closer and closer and closer together. When I slow down to the left, I need an arrow pointing left. Read this from right to left, and I see the dots are getting closer and closer together. Now let's talk about what the graphs look like. On a position time graph of no motion, it should be any horizontal line segment. If I'm traveling to the right with a constant velocity, I need any diagonal line with a positive slope. If I'm traveling to the left with a constant velocity, it is any diagonal line with a negative slope. When I speed up to the right, I need the graph to go up and get steeper. So any parabola that goes up and gets steeper. When I speed up to the left, I need a parabola that gets steeper and goes down. Any parabola that goes down and gets steeper. When I slow down to the right, I need a parabola that goes up but levels off. When I slow down to the left, I need a parabola that goes down and levels off. And lastly, let's look at these velocity time graphs. When I'm not moving, my velocity graph must be a horizontal line on the 0 velocity value. That's the horizontal axis. Constant velocity to the right is any horizontal line up above the x-axis. Constant velocity to the left is any horizontal line below the x-axis. Speeding up to the right is a diagonal line. It has to be above the x-axis and moving away from the x-axis. As I speed up to the left, I need a diagonal line which goes down in the 4th quadrant below the x-axis. As I slow down to the right, I need a diagonal line up in the 1st quadrant which approaches the x-axis. When I slow down to the left, I need a diagonal line down in the 4th quadrant which is approaching the x-axis. Okay, that gets us through all the patterns through page 31. Let's now look at page 32 and 33, which are about the term acceleration. So define an acceleration in your own words. It's the rate of change of your velocity. What kind of quantity is acceleration? It's a vector, and it must include both magnitude and direction. Number 3, the equation for average acceleration is change in velocity over time, or VF minus VI over T. The units for acceleration are either meter per second or meter per second squared. The 3 ways you can accelerate are by speeding up, slowing down, or changing direction. If your initial velocity and your acceleration are in the same direction, you are speeding up. If they are in opposite directions, you are slowing down. A constant acceleration refers to a constant rate of change in your velocity. An instantaneous acceleration refers to how quickly your velocity is changing at one specific moment in time. And an average acceleration is how your velocity changes over a period of time. For our course, all three of these would be the same. Again, in our course, we limit our discussion of acceleration to constant accelerations, which would be the same as the average acceleration, which is the same as the instantaneous acceleration. We do not deal with changing accelerations in this course. Number 9, how do initial velocity and final velocity differ? Your initial velocity is your velocity before you accelerate. Your final velocity is after you accelerate. Another way to say that is your initial velocity is at the starting time. Your final velocity is at the ending time. Number 10, there are 6 equations that you should know, not 4. There are 6. They are VF is VI plus AT, D is VIT plus half AT squared, VF squared is VI squared plus 2AD, A is change in V over T, V bar is D over T, and V bar is VI plus VF over 2. I know it asked for 4, but there's actually 6. So you should know all 6. Those are in no particular order. All right. All the rest of this is multiple choice. So let me start giving you answers to all the multiple choice. And once I finish giving you the answers to all the multiple choice, you can ask questions. So on the first page, 1 is D, 2 is D, 3 is A, 4 is B, 5 is D, 6 is A, 7 is C. 8 is D, 9 is A, 10 is B, 11 is D, 12 is D, 13 is C, 14 is C. 15 is C, 16 is A, 17 is C, 18 is B, 19 is D, 20 is D, 21 is B, 22 is A. "23 is A, 24 is B, 25 is A, 26 is A, 27 is C, 28 is B, 29 is A. 30 is A, 31 is A, 32 is C, 33 is C, 34 is A. 35 is B, 36 is B. 37 is A, 38 is C, 39 is D, and 40 is A. All right, the last 2 pages. Number 1 is 3, 2 is 4, 3 is 2, 4 is 3, 5 is 2, 6 is 3, 7 is 4, 8 is 2, and 9 is 4. Now, when you want to ask questions on these multiple choice, I'm going to ask you to first give me the page number that the question is from, and then the question number, okay? Anything you want to go over? Eric. All right, so which pair of graphs represent the same thing? This one here? All right. So let's go through each one. This is just patterns. You should be able to tell me what's happening. When I look at a distance time graph and I see the distance is not changing over time, this shows me that I am not moving. This one shows me speeding up. The graph is going away from the time axis. I'm going to bigger and bigger numbers. So A is not right. If I look at B, this one shows the graph going up, which means I'm traveling to the right, and it's leveling off, which means I'm slowing down. So this is slowing down as I go to the right. This one shows that my speed is not changing. So here I have a constant speed. Slowing down and constant speed are not the same things. C shows a parabola, which is going up, which means I'm traveling to the right, and it's getting steeper. So this one means I am speeding up as I go to the right. This one shows that the speed is getting bigger and bigger and bigger as time goes on. So this is also speeding up. Speeding up, speeding up. Now, if I look at this one shows me a diagonal line, which shows me that my distance traveled over time is happening at a constant rate. So this one would be a constant speed. This one shows me speeding up. The numbers are getting bigger on the speed axis. So that's speeding up. You can't have both of those. So that's why it's C. Anything else? Lila. The last two. So 1 is 3, 2 is 4, 3 is 2, 4 is 3, 5 is 2, 6 is 3, 7 is 4, 8 is 2, and 9 is 4. Okay. You all set? 3, 4, 2, 3, 2, 3, 4, 2, 4. Yep, Chang. Page 40. Number 38 and 39. Okay, and these questions all come from this graph here, which is a speed time graph. Notice it says 37 through 40 are all based on this. Tells us that we're starting from rest here, gives us some information about how the objects are moving. 38 asks us how far car A travels between 0 and 60 seconds. How far means I'm looking for the distance, which on a speed time graph is equal to the area. And I'm looking for car A. So here is car A. If I were to calculate that area, here's 60 seconds. I'm looking at that triangle that's right there. So how do I find the area of a triangle? I do 1/2 the base times the height. The base is 60 seconds and the height is 60 meters per second. So that's 30 times 60, which is 1,800 meters, choice C. That's one way to do it. The other way to do it would be to use that the average speed is the distance over the time, or the distance is the average speed times the time. Now, to get the average speed, I can calculate it by doing VI plus VF over 2, or I can just read that average speed by looking at the velocity at the middle time, which the middle time would be 30 seconds. So if I read the graph at 30 seconds up and over, I see that the speed is 30 meters per second. That's the average speed. So I could do this by taking 30 meters per second and multiplying by the length of that time interval, which is 60 seconds. 30 times 60 is 1,800 meters. So I could do it either way. Okay, either way. Now, number 39 asks us, how long after time 0 does it take car A to catch up to car B? When the two cars catch up, it means that the distance traveled by A is equal to the distance traveled by B. So if I think about that area idea, I can do this visually. I see that between 0 and 30 seconds, I'm going to start shading in B in purple here. Here is B. The area traveled by B is that large rectangle between 0 and 30. Do you notice how that's always going to be bigger than the area for A beyond that? I have to get beyond 30 seconds in order for the two areas to be equal. And where that will happen is at 60 seconds. Now let's look at why. Car B all the way to 60 seconds would give me this rectangle all the way to there. Do you see how car A, we had this extra triangle up here? If I were to rotate that triangle, it would fit exactly in that area right there. That's when those two areas would be equal. And that's the time, therefore, that we're looking for at 60 seconds. So you can do these visually when you start shading things in on the graphs. Very often you don't have to calculate anything. You just have to look at it and say, oh, where's this area? How do these pieces fit together? Anything else you want to ask on any of that? Hudson.
Page 36. 22.
You got it. Let's look back at that page. 3622. Okay. To answer these two questions, it's imperative that you read the paragraph above the graph. Okay, it says that we have a cart here, initially at rest. We can see that because the velocity starts off at 0. But then do you see what it tells me? That we start going northward. So north is the positive direction. So everything in this quadrant would be north. And that means everything down here is south. Okay, so I want to know in what direction we're traveling at 4 seconds. All you do is you read the graph and figure out what quadrant are you in. 4 seconds, go up. Over, I see I'm in the north area. That's a positive 10. So that means I have to be going north. This cart would not be going east and west. Why? Because it says I've got north, so I've got north and south only. Colin? Sure. 21 asks us at which value of time t are we back at our starting point? When you're back at your starting point, that means your displacement is equal to 0 meters. Displacement is area on these graphs. The horizontal axis is here. And I notice that anywhere between 0 and 5 seconds, I'm going to end up with a positive amount of area. That area is positive. It's not 0. In order to get a 0 area, a 0 displacement, I'm going to have to add something negative to this positive amount, which means I need to go beyond 5 seconds. So look at the choices. Do you see how there's only one choice beyond 5 seconds? That's at 8.5 seconds. Now let's look at why that is. Here is 8.5 seconds on the graph. There is the area. It's below the x-axis. That area is a negative area. And it would just so happen, if I calculated it, which I'm not going to, that this positive amount and this negative amount should be exactly equal. And that would give me a 0 displacement. The only choice that makes any sense is this one, because that's the only one that would allow us to add a negative amount of area to a positive amount that can possibly give us 0. Do you all understand that? Okay. I know in math they say you can't have negative area. This is not math. This is physics. That negative means something. Beyond 5 seconds, we started going south. We were headed north. At 5 seconds, we stopped in reverse direction. So the only way we can get back to our starting point is after we have reversed our direction to get us backwards. And that's why it's going to be over here. Make sense? Okay. Anything else?
Can you go over question 3 on page 41?
Yep, page 41, number 3. Okay, these are done using your guess method. Okay, in order to, obviously it's multiple choice, you don't have to do a check. But let's look at what it tells us. We're initially traveling at 20 meters per second in the west direction. Usually we say that west is a negative direction, left. Now, you're not going to see this word on any exams that I give you. Decelerates was eliminated from the Regents curriculum in 1996. So instead, you're going to see that it tells you it slows down. And when we slow down, our acceleration is always opposite the direction we're headed in. So that means this value here for the acceleration would be opposite of west or east, which is positive. And then we have a time. I'm looking for displacement. So in terms of my givens, I would say that the VI is negative 20 meters per second, because that negative means west. Since I'm slowing down, the acceleration is the opposite direction, which is positive here, 4.0 meter per second squared. And the time is 2.0 seconds. My unknown is the displacement. So now we go to page 6 of your reference table. I don't expect you to have these equations memorized. I do expect you to look them up. So we look at those equations that we've got checked off and added on. And the only one that has those 4 variables is this one here. So that's the equation I'm going to pick. I'm now going to plug in. So that's negative 20 meters per second times 2.0 seconds plus 1/2 of positive 4.0 meter per second squared times 2.0 seconds squared. So let's just do the math. I don't even need a calculator to do this. Negative 20 times 2 is negative 40. Half of 4 is 2. 2 squared is 4. So 2 times 4 is 8, and that's positive 8. What do you get when you add negative 40 to positive 8? You get negative 32, and this is meters. What does that negative sign mean? It means west. So there is my answer, 32 meters west, choice 2. Yeah, let's look at the dimensional analysis on this. So you start with the equation that you plugged into, and I encourage you to rewrite that equation. A lot of you didn't do that yesterday, which means you messed some things up moving forward. I didn't take off for that, but I do recommend you rewrite the equation you plugged into. Now you change everything out to the units that you expect. D was in meters. VI was in meter per second. T was in seconds. Half does not have a unit. This has everything to do about units. There are no numbers. So ignore that half. Ignore it. A was in meter per second squared. T was in seconds, which must get squared. Now you have to show how this equals that. You can't just say meters equals meters. You have to show me how you get there. This cancels that. This cancels that, leaving me with some amount of meters added to another amount of meters. The answer isn't 2m. This is not what you do in math class, where that's a 1 and that's a 1. There are no numbers. If I had an amount of meters added to another number of meters, I'm going to end up with a number of meters. Notice both sides check. That is how we do the dimensional analysis on that equation. See Chang. Yep, page 42, number 9. All right, we have an object initially traveling at 20 meters per second south. Again, you are not going to see the term decelerates. What are you going to see? Slows down. At 6.0 meters per second squared, it gets displaced 25 meters. I want to know the final velocity. South is usually a negative direction, right? That's like down in the XY axis. So let's list our givens. The VI would be negative 20 meters per second. The acceleration must be positive because it's slowing down, opposite the direction of the velocity. So positive 6.0 meters per second squared. Now think about this for a minute. If you're going south and you're slowing down, which way did you end up moving? South, right? So the displacement should also be negative 25 meters. Your unknown is the final velocity, VF. So the equation that I'm going to pick that has VIA, D, and VF, doesn't have time, is this one. VF squared is VI squared plus 2AD. Now, to get VF, I need to take the square root of both sides. So that is the algebraic manipulation. Remember that whenever you do a square root, you have to decide on a direction, positive or negative. That's going to matter here. You were going south, you slowed down. Which way are you headed after you slow down? Probably in the same direction, the negative one, okay? So I want the negative root. So that is negative 20 meters per second squared plus 2 times positive 6.0 meters per second squared times negative 25 meters. Now this one, I am going to go to my calculator to do it, just to make sure I don't mess it up. So negative 20 squared, I'm not even going to, let me put that parenthesis there. Plus 2 times 6 times negative 25 gives me 100. What's the square root of 100? 10. So my final velocity is negative 10 meters per second, and that negative sign means south. So I need to be going 10 meters per second south, choice number 4. Now, understanding that it says slows down should have helped you eliminate 1 and 2. Because what would those have been? Are those slowing down? No, those were speeding up. So it had to be either 3 or 4. And that's why we get 4. Because when you slow down as you're traveling south, you're still going south. Eric?
So I did it where it was VS squared equals like VS squared in the equation, but I plugged everything in, I think the square root.
That's going to lose you points tomorrow. Yep, because you have to do the algebraic manipulation first.
Where did the negative come from?
The direction, which means south. It says south. South is a negative direction.
I'm talking about like you started solving it.
Because I have to think, when I'm headed south and I'm slowing down, which way am I headed after I've slowed down? Still south. Negative. Outside of square root, you can get a plus or a minus. You have to decide which one it is. That's why I say you got to think about it. Your car didn't all of a sudden just turn around after you stepped on the brake to slow down. You're still headed in that southerly direction. Anything else? Right.
Other than outside of square root, is there any other time that you have to think about?
No. No.
And I don't know.
Yep.
It's not on the
That's okay.
It's page 31.
Page 31. Okay. On the pattern stuff. Yep.
For slowing down to the right and slowing down to the left, I don't understand the velocity behind that.
Okay. So when you slow down, that whenever you see the word slow down, that means your speed approaches 0 until you stop. You got to get closer to 0 for the velocity. Because eventually, after you've slowed down, what does your velocity equal? You step on the brake on your car is eventually going to stop, which means eventually you get to a velocity of 0. Okay, so both of those need to get close to 0. Where is 0 on your velocity graph? Right there. This is a 0 value. We need to get closer to it. Now, the first one says that we're going to the right. Right means we have to be up here. So the number has to start big and get close to 0. The number has to start big. If I'm going left, it has to be down here. It's got to be a big negative number and get close to 0. Make sense? Okay, because the number itself is your speed without the sign. The sign just translate it to a word, right or left, or north or south, or east or west, any positive or negative direction. Yep, Su Chang. I'm sorry, what number on page 37? 23. Okay. I want to know in question 23, which one travels the greatest distance? On a speed time graph, that's the area. So we're going to shade these in. Okay. I'm going to start with car D because car D is the lowest line. There's my horizontal axis. The area would be there to 16 seconds, right? Between 10 and 16 seconds. So that's the area for car D. Car C, let me do this one in purple. There's car C's line. I got to shade all the way down from here. C travels more distance than D did. You see why? It gives me a bigger shape than that curved area. There's B. I got to shade all the way down to the horizontal axis. There's B. That travels even more distance. What about A? There's A, which means I would shade in all the way down for A. Which one gives me the biggest shape? A. Therefore, it is car A. Again, you don't have to calculate anything. Anything else?
Go over 8 on the last page.
Yep. So page 42, number 8. Okay, we're initially going 10 meters per second north. We accelerate at 3.0 meters per second squared to the north for 4.0 seconds. I want to know the displacement. North is a positive direction. So when I list my givens, the VI is positive 10 meters per second. The A is positive 3.0 meter per second squared. The T is 4.0 seconds. My unknown is the displacement. The best equation, which has VI, AT, and D, is D is VIT plus 1/2 AT squared. My guess is you probably forgot to square the time. So this is positive 10 meters per second times 4 seconds plus half of positive 3 meter per second squared times 4 seconds squared. So 10 times 4 is 40. Half of 3 is 1.5. 4 squared is 16. So 16 times 1.5 is 24, which gives me positive 64 meters. That's 64 meters to the north, choice 2. All right, that's the end of our review. I will be after school today until 2:45 if you want to come in for some more help on this. Right now, let's take our break. When we come back, we're going to start Unit 4. All right, Noah, put your Chromebook away. Use your reference table, your pencil, your calculator, and pull your notes together. This question makes sure you follow directions.
I went to the bathroom, but the line is too long, so can I make a password and so I can go?
Yeah. I'll get it to you at the end of the period, okay?
Can I go back to the, at the end of today? After that?
Yeah, that's fine. Yeah, that way you don't have to carry it around, right?
Yeah.
Yep, no problem. All right, ladies and gentlemen. You can't initiate it?
If they don't give me the option.
Yeah, it's not an automatic. Let's cancel this in 5 minutes. Can you cancel that one and initiate another one for 5 minutes to that chemistry one? All right, ladies and gentlemen, everything away except your notebook and your reference table. Something to write with, of course. We're going to start Unit 4A now. Unit 4 is super short. 2 sections, A and B. Bryce, Chromebook away. It's very short, 2 sections, A and B. You will have a test on this a week from tomorrow. And then you'll have a quarterly exam on Friday, which covers units 1, 2, and 3. Tomorrow, after you complete your test, I will give you the review packet for the quarter exam, which is on units 1, 2, and 3. This will not be on the quarter exam, but it will be tested next week, and it will be your first test grade for the second marking period. Okay? All right, let's get started with kinematics and free fall, unit 4. We're going to start off by talking about objects that just fall. That's all we're talking about. We're still talking about accelerated motion, but we are no longer dealing with objects that are moving parallel to the ground. We're dealing with objects that are now accelerating in the vertical plane. Specifically, right now, we're going to talk about them dropping. And if you've been to some large amusement parks, these pictures came from not the one in New Jersey. The Great America is Six Flags Great America, I think, is in Texas. These 2 pictures are a ride that they have there where you're brought up to the top of a tower, strapped in, and then they just release you until you're about 2 stories above the ground when they then apply the brakes. So that way you don't slam into the ground. But that's a free fall ride. So we'll be doing some questions dealing with free fall ride. These are the things I'll expect you can do when we deal with a dropped object. Basically, it's everything that you should be able to do for tomorrow's test, but not applied to objects that are dropped. They're applied in the horizontal plane. So what is an acceleration? You should be able to define that. We're going to talk about one specific acceleration that deals with a dropped object called the acceleration of gravity. I'll then ask you to explain what is meant by free fall. You'll be asked to use graphs and equations to describe these objects that are falling. Of course, correctly use our 7-step problem-solving method to then solve problems involving dropped objects. So let's talk about what the term free fall means. Free fall refers to more than that. It refers to more than that object that's dropped. What does free fall refer to? It refers to anything that's being acted upon solely by gravity. The word "sole" means only. Only gravity is influencing how the object moves. In other words, we're not going to have any air resistance to consider. Can we actually deal with free fall here on Earth in the real world? No, because we have air around the Earth, which contributes to air resistance acting on things. But in order to understand how things fall with air resistance, you first have to understand how they fall without air resistance. We also will not deal with problems involving air resistance in this course other than conceptual, because you need to use calculus to solve problems with air resistance. And that is not a requirement of this course, just algebra and geometry. So when we deal with something in free fall here on Earth, what that means is that they are accelerating downward at about 10 meters per second per second. If I want to be precise about that, we're going to use a value of 9.81 meters per second to describe that acceleration. Is everybody all set with that? All right. So let's do this little hypothetical experiment. And I say hypothetical because we can't actually do this here on Earth. I want you to imagine that I have a hammer and a feather. So imagine that this is my hammer, this is my feather. I'm going to drop them from the same height at the same time. All right, you can envision that, right? Okay. Now, suppose that air resistance can be eliminated. Somehow or other, I have evacuated all of the air in this room. We have a problem because now we can't breathe. But let's just say all the air all of a sudden disappeared. And I dropped them. So neither one experiences any air resistance or air drag as they fall. I want to know which object, the hammer or the feather, hits the ground first. Now there's 4 possible answers. Either the hammer hits first, the feather hits first, they hit at the same time, or neither one gets to the ground ever. I want you right now to hypothesize what you believe happens. Go ahead and write down your hypothesis about what you believe would happen. So yes, yeah, we didn't turn off gravity. Gravity is still there. We just got rid of the air. What happens? Write down your hypothesis, and you can write down hypothesis. What happens? Which one hits the ground first and why? Why do you think that happens? Okay, everybody has something written down? All right, I want to know, how many of you think the hammer's going to hit first? How many of you think the feather hits first? How many of you think they hit at the same time? How many of you think neither one gets to the ground? Okay, so let's find out. I'm not going to get rid of all the air in the room. Don't worry. You're still going to be able to breathe. We have actually done this experiment on the moon. It was done in the Apollo 15 mission, which was early 1970s. All the Apollo era missions were designed to get to the moon. So we've been there before. We're trying to go again. And here's a little video clip of the astronauts doing this experiment.
Well, in my left hand, I have a feather. In my right hand, a hammer.
There's the hammer, there's the
I guess
feather.
one of the reasons we got here today was because of the gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? My conclusion, Mr. Galileo was correct in his findings.
All right, so obviously we saw in that video clip that they both hit at the same time. So congratulations to those of you who made the correct hypothesis. Let's now talk about why that happens. First of all, we need to understand some differences between the Earth and the moon. The Earth has a very thick atmosphere that surrounds it. What does that mean? It means there's lots of very large molecules of gas, specifically oxygen, nitrogen, carbon dioxide. These are very large molecules which create a very thick atmosphere. And those big molecules create a lot of air resistance as objects try to move through the air here on Earth. Now, a misnomer is that people believe there is no air around the moon, and that is incorrect. There is air, but the air is very thin. The air that surrounds the moon has much smaller molecules. Therefore, there is effectively almost no air resistance on the moon. One of the reasons the astronauts, when they go to the moon, wear spacesuits, there's several reasons. One is for the air. They need a very oxygen-rich air supply in order to breathe, as do you. So their suits have those oxygen tanks that allow them to breathe in the air. Another reason is because there is no magnetic field around the moon. So once you leave the Earth and you leave its magnetic field, you are being bombarded with cosmic radiation from the sun. That's direct solar radiation, which would burn your skin very quickly. You would end up with a really, really, really bad sunburn almost immediately. The other thing that not having that magnetic field does is it creates a very cold environment around the moon. So that suit is protecting them not only from the radiation, but also from frostbite like that. Okay, so that there's a lot of reasons we have that. But in terms of the air, the moon has very thin air, so there's very little air resistance. So without air resistance, we can get objects regardless of their size, their shape, their mass. As long as they are dropped from the same height at the same time, they hit at the same time. Now, I can actually demonstrate this for you here in class without getting rid of the air. And let me show you. I'm going to do this with a textbook and a piece of paper. I think we all know what would happen if I dropped the textbook and this piece of paper like this. Which one would get to my desk first? Sure did. And we see the paper sway, right? Why does it sway? Because there's a lot of air resistance acting on this. The way I can get rid of that air resistance on the paper is by doing this. I'm not changing the paper other than changing the surface area that is colliding with those air molecules. Now, when I do this, watch what happens. Which one got there first? Same time. They now hit at the same time once I minimize the amount of air that's acting on the paper. This was first theorized by the scientist on the top left, Galileo Galilei. He lived from 1564 to 1642. That's during the Renaissance era. And he was Italian. He did some experiments at this site right here. Do you know what that is? Leaning Tower of Pisa. Now, according to legend, Galileo went to the top of this tower with two different cannonballs. One was 10 times the mass of the other. And he dropped them off to see what would happen. They were the same size, but one was 10 times heavier. Apparently, he did this in 1585. Now, you notice I say it's according to a legend. I don't actually believe he did it. Let me give you some reasons why. Has anyone ever been to Pisa? I went there the summer after my junior year of high school. My family, I still have a lot of family in Italy, so we went to go visit my aunt, my uncle, and a bunch of my cousins. And part of that, my parents said, oh, we're here. We spent a month there. We went to all the different little big tourist attractions, like Pisa, Italy has the tower. We said, if you're going to go to Italy, you might as well go see this. You got to go to Venice. You got to go to Rome and see the Colosseum, those kinds of things. So we went there. This was not as impressive as I thought it was going to be. It's about as tall as the towers of Colony, the apartments. That's about as tall as it is. And when you go, if you go now, they have it all roped off. Miss Creasy went there this summer, and I think she was actually able to go in. They've now stabilized the ground so you can go in. When I went in 1991, it wasn't stable. We couldn't go in. But the doorways around the outside are really small. They're about half the width of the door we have here to our classroom. One of the reasons I don't think Galileo did this is because if you read anything about Galileo, he was a very large man. Okay, so for him to be able to get through a narrow doorway, I don't think would be easy for him. The other reason I don't think he did it is because, again, if you read anything about Galileo's life, you will learn that he was very ill for most of his life. So for a person of his stature and his mental condition, I don't think he would have been able to climb 15 sets of stairs to the top with two cannonballs, one 10 times heavier than the other. I just don't think he would have been able to do it. But he was very wealthy. So what did he probably do? He paid somebody. Probably not with money, but probably with food. You learn about back in those days, you were dirt poor. You didn't have anything to eat. So he would give somebody food and they'd be thrilled and they would go do it. So I think what he did was he observed from the side what was happening instead of himself going to the top of the tower and dropping these 2 cannonballs, just releasing them. As I said, one cannonball was 10 times more massive than the other. And what he observed was that both cannonballs landed at exactly the same time. Since they had the same shape and they were the same size, they had the same amount of air resistance force acting on them. So he saw that doesn't matter what the air resistance is, objects will land at the same time if we can neglect the effect of air resistance. Okay. Kind of amazing for someone back in those days when there's no technology to be able to start to develop. He actually came up with all the equations that we've been using so far. All of those kinematics equations were developed by Galileo Galilei back in the late 1500s. So what Galileo was able to do was he proved that this value of lowercase g is a constant, regardless of how massive or how dense the falling object is. So what is his big contribution to this unit is that all objects fall with the same acceleration regardless of their mass. That's the key right here. All objects fall with the same acceleration regardless of their mass. And that acceleration is a value that we give a constant letter, lowercase g, to. So we'll be looking at that on our reference table in just a minute. Okay, is everybody all set with this slide? Anyone need more time with that slide? Okay. So let's just investigate a little bit more about air resistance and where it comes from. This is the extent of what you'll need to know. You can see that here when we do an experiment with something that's more massive than the other, that in this case with air resistance, the more massive object, in that case, the elephant gets to the ground first. Why does that happen? Air resistance, as I mentioned earlier, comes from the collisions of the surface of the object with the air molecules as it falls through. Things are actually hitting. And those collisions slow down the movement of the falling object. The amount of air resistance objects experience depends on, it's really 3 things, but we're just going to focus on 2. First of all, how fast you're moving, the speed, and the cross-sectional area of the object. I demonstrated for you a moment ago that if I reduce the surface area that's in contact with the air, I can eliminate the effect of air resistance. We saw the effect of the surface area. To understand how speed affects air resistance, you can do a really simple experiment on your own. In your car, I want you to drive along with the window open. Stick your arm out the window. Go very slow, like 2 miles an hour. Feel the air pushing against your hand. Then speed up to 15 miles an hour. At 15 miles an hour, you're going to feel a lot more air pushing against your hand, pushing it back. That means there is more air resistance. So it's related to the speed and the surface area of the object. One area that mechanical engineers work on when they are designing cars is trying to minimize the effects of air resistance on vehicles. I shouldn't just say cars. They do this with airplanes. They do it with any object that we want to move, that especially if we're powering it by gasoline. We want to try to make them more energy efficient. So they work on designing the shape so it is more aerodynamic, which just means it's affected less by air resistance. Okay, can I go on? All right. So let's now talk about the nitty-gritty. When we deal with an acceleration due to gravity, here on Earth, we're going to deal with a very specific numerical value. So the acceleration due to gravity is a very specific numerical value for the acceleration of an object in free fall. We're going to deal with it primarily on the Earth. And as I mentioned to you on a couple of slides ago, we use a special symbol because it's a special number. The symbol that we use to represent this particular acceleration is a lowercase g. Lowercase. Please make sure it is not uppercase. There is a different value for uppercase g. So you got to make sure you do a little g, not a capital. Now, I'd like you all to turn to page 6 of your reference table because we're going to check off that symbol right now. On page 6 of your reference table, look in your right-hand column and you'll find the little g. Check that off. This is a value for the acceleration due to gravity. Whenever I use that little g with you, it's a specific acceleration value. But it's the acceleration that comes from gravity. So just go ahead, check that off there. Now, what we're going to do is now go to page 1 of our reference table, and you'll see the value for it on page 1. The value we're going to use for Earth is 9.81 meters per second, and it's directed downward. So let's go back here. Page 1, you'll see it's the second value in the chart. Go ahead, check this off. This is going to be, as we can see, in meters per second squared. And there is our value, little g. This is the value. It is a vector. So we have to understand that it also has a direction, and that direction is down. So please add that. It is directed down. Okay. Down is usually a negative direction. So when we use it in problems, we usually make it negative. Okay. Now, this value of 9.81, just to be ultra technical about it, is not the value that we have here in Albany. We're a little bit above sea level. 9.81 would be the value at sea level. We see slight variations in this due to altitude. The higher up you go, the smaller that number becomes. So if you lived in Denver, Colorado, you're probably using a value of like 9.76 meters per second squared instead of 9.81. They're about 2,000 feet above sea level there. If you lived in Louisiana, in New Orleans, they're below sea level there. That value is a little bit more than 9.81. It's probably like 9.82 meter per second squared. We will learn later in this course that that value gets smaller as we get further from the center of the Earth. It's dependent on our distance from the center of the Earth. Now, if you're doing a multiple choice question, a little hint here, you can make your life easier if you approximate this number to 10 meter per second squared. With one sig fig, 9.81 rounds to 10. And it's a lot easier to multiply and divide by 10 in your head than it is to do that with 9.81. So you should be able to do simplify the math and just look for the best choice, the closest answer when you're doing multiple choice. If you just round it to 10 meter per second squared instead of 9.81. If, however, you need to be precise, like a show work question or a lab, you have to use 9.81. You cannot approximate it, okay? Is everybody all set with that? So show work questions, laboratories, use 9.81, not 10. All right, let's now go through all of the things we learned about acceleration, but apply it to falling. This is what a ticker tape diagram would look like for an object that's falling. So I would put an arrow next to this pointing downward because that's the way this object is moving in the downward direction. We see that the dots are getting further and further apart as it goes downward. What does that indicate? It indicates that it is speeding up in the downward direction. So we see that the distance traveled every second is going to increase in that downward direction, which indicates that we are speeding up as we fall. Remember that whenever you're speeding up, your velocity and acceleration will have the same directions. So since our velocity is down, that's the direction we're moving in, down, the acceleration is also down, which makes sense. We just checked off 9.81 meter per second squared going down. You may want to add that ticker tape to your notes so you remember what it looks like. We're also going to add some numbers to it in just a minute. If those dots are at 1 second intervals where the top dot is at 0 seconds, we would have 0, 1, 2, 3, 4, up to 5 seconds of traveling. All right, can I go on? All right, so that's like the basics of what we learned about when we started talking about acceleration. Now let's get a little more quantitative. Remember that when we define an acceleration, we're talking about how quickly your velocity changes. How quickly does your velocity change? So if we have an acceleration that's about 10 meters per second, that means our velocity is changing by 10 meters per second every second. So this is what a data table would look like here on Earth if I was just measuring to 1 sig fig for something that's dropped. Something that is dropped at time 0 is not moving. Its velocity is 0 meters per second. But the speed needs to change by 10 every second. So notice that I go from 0 to 10 to 20 to 30 to 40 to 50 meters per second over 5 seconds. What does the negative sign on those velocities mean? Down. So we were moving downward at 10 meters per second, downward at 20 meters per second, and so on and so forth. We can see when we look at that velocity table that the acceleration is about negative 10 meters per second. Here are the speeds labeled on our ticker tape. 0, 10, 20, 30, 40, 50, all the way from 0 to 5 seconds. We can see that we are speeding up as it moves downward, and the downward is the negative direction. Those are speeds, not velocities, but we can see that the speed is increasing, but it's going down, so the velocities would end up being negative. Does that make sense? Okay, so that gets through the first part of what we learned about with acceleration. Now we have to start to talk about what the graphs look like. Let's start with our position time graph. This is a sketch of a position time graph for an object that's dropped. Now, what can I see from this position time graph? I can start off by telling you from what height it was dropped. You know how I do that? I just read off the y-intercept. The 0 meter position is the ground. That y-coordinate there, the y-intercept tells me the starting height. Notice that we get a parabola on this graph. A parabola on a position time or displacement time or distance time graph indicates that the object is accelerating. Notice that slope is velocity. So when I look at this, I see that I start off with a horizontal tangent line. That means I start off at rest. The initial velocity is 0 meters per second. But as time goes on, that graph is getting steeper, which means that the velocity is increasing. Since the graph is headed down, those are negative slopes, which tells me that I have a negative direction, therefore a large negative downward velocity at the ending time. Again, you may want to indicate that the y-intercept gives you the starting position or the height that it's being dropped from. That's your starting point. The x-axis, 0 meters, tells us that that is the ground. The 0 meter position is the ground. Okay, can I go on to the next graph? The velocity time graph. Let's look at what the velocity time graph looks like. The velocity time graph has to be down in quadrant 4. Why? Because all the velocities are negative, except for the starting one. The starting velocity is 0 because it starts from rest. We expect a diagonal line on this graph because a diagonal line on a velocity time graph indicates the object is accelerating. If I read off from the graph, of course, I can read my initial velocity at time 0. The y-intercept is 0 meters per second. Notice that I end up with a very large negative final velocity. The number's really big, and it's negative, indicating that I went downward. Since the graph is going away from the time axis, I know I'm speeding up. I'm going from 0 to like 50 meters per second. That's what we saw on the ticker tape. That's speeding up. The negatives just tell me it was headed down. Negative in this unit means down. Positive would mean up. Remember as well that the slope of that graph would give us the acceleration of the object that's dropped. So in this case, we would expect a slope that's about negative 10 meters per second per second. To be precise, that would be negative 9.81 meters per second squared. All right, so that talks about the graphs. The last thing we have to talk about is the problem solving. So whenever we do problem solving with dropped objects, oh, hold on, couple more things here. The slope is the acceleration. We see the slope doesn't change as we go. So that means we have a constant acceleration. That slope is negative, which means our acceleration is also negative or downward. Right, the slope in the beginning of the graph is the same as the slope at the end of the graph. The steepness is not changing, so therefore the acceleration is not changing. All right. Okay, so let's tackle the guess method stuff. The kinds of questions you'll be asked are things like, how far did this object fall in 3 seconds? Or how fast was it moving after 3 seconds of falling? Whenever you solve these questions near the surface of Earth, there are 2 things you're going to have to list as givens that are not going to be told to you. The first is for all objects that are dropped. Whenever we see that something is dropped, that word dropped means it is starting from rest. The VI is 0 meters per second. You have to know that. And you should be listing that as one of your givens. The other given that you will not be told comes from the fact that it says you are on Earth. Because we are on Earth, it means we also know what the acceleration is. It's that acceleration we just checked off on page 1 of our reference table. 9.81 meter per second squared going down. Remember, we make down a negative sign. We don't say negative 9.81 meter per second squared, comma, down. You either say down or you put the negative sign. You don't do both. The negative means like opposite. So opposite of down. If you wrote negative and down, you actually mean up. Gravity's not pulling you up. I've never seen a pencil released that goes up in the air on its own. Okay? That's the end of the presentation. What we will do on what is today? Tuesday? Thursday, our next double. We are going to finish up this topic with solving the problems in your packet that are there for practice on falling objects. Tomorrow, all we're doing is taking your test on Unit 3. And for that test, remember that you need to bring a pen, a pencil, a ruler, and a calculator. It's a 1-period exam. And when you finish it, you're going to give me the test, and then I will give you your quarter 1 exam review packet, which will be due in a week.